Hello. In the previous lecture, we looked at a motivating example for the Lyapunov functions, and then we started off looking at some definitions that we'll come across. We looked at the positive definite, where the function v of x is strictly positive. It is positive semi-definite if it's positive but is equal to 0 at certain points. It is negative definite if this is strictly negative, and negative semi-definite if it is negative or equal to 0 at certain points. Okay, so these are some definitions that we'll come across with. Here are some two useful examples. So the function v, which is a function of x1 and x2, equal to c1 x1 squared plus c2 x2 squared. So this will be positive definite. Of course, for c1 and c2 positive, this will be positive away from 0, 0. So it is said to be positive definite. V here is in R3. You have x1, x2, x3, but it's equal to c1 x1 squared plus c2 x2 squared. There is no x3 here. All right. So we see that on the x3 axis, right? On the x3 axis, x1 and x2 are 0. But away from the x3 axis, where c1 and c2 are positive, this function is going to be positive. So v is either positive or 0. It's positive away from the x3 axis, and is 0 on the x3 axis. So this is positive semi-definite. Okay? So this is a useful example to keep in mind on positive semi-definite functions. Or on the other hand, negative semi-definite. Okay, good. So here is the main theorem for our Lyapunov function. It says consider an orthonormal system. It's the same system that we saw before, with an isolated equilibrium point, x star. Isolated means that it's just a point, a single point, and it's not, for instance, it's not a line of equilibrium points, right? There are times you can have a whole line of equilibrium points. This is not the case. We are looking at points. Okay, so it is an isolated equilibrium point x star. Let omega be an open set containing the equilibrium point such that v is a smooth function. All right, and number one, we want v, this function v here, v at the equilibrium point to be equal to 0. So this is important. And v has to be positive away from the equilibrium point. All right, if x is within omega but x is not equal to this, then this has to be positive. So this is how you define, when you are defining or constructing a Lyapunov function, you have to make sure these conditions are satisfied. At the equilibrium point, your Lyapunov function must be 0, and away from the equilibrium point, it has to be positive. Okay? Good. So one has to be satisfied. Now, one is satisfied, then 2 says that for every solution x of the system, taking values in omega, if the derivative with respect to time, this is the total derivative with respect to time of v, is negative semi-definite, right? It's less than or equal to 0, then x star is a stable equilibrium point. If the derivative is strictly positive or positive definite, then x star, that's the equilibrium point, is an unstable equilibrium point. If the derivative is strictly negative, right, it's negative definite, then x star is an asymptotically stable equilibrium point. Okay, so again, the difference between 3 and 1 is that you can go back to this example, in the case where you have the function in R3, that is possible, right? That it is 0 at certain points, but it's negative at certain points in other points. And it's also possible to be strictly negative without being 0. All right? Okay. So basically, this is the Lyapunov, the theorem for Lyapunov functions that we are going to use. All right? We're not going to prove it. We're going to apply this. Okay? So you should understand how this theorem works and how it is applied. We'll do some examples to illustrate it. But before that, I need to make an important remark here. So note that by the chain rule, the total derivative, right, v, with respect to t, all right, which I'm calling v star here. This you can rewrite as the partial derivative of d with respect to x1 multiplied by the x1 dt plus partial v with respect to x2 the x2 dt, and so on until you get to this point xn, right? And this you can combine to be the sum of partial v partial xi multiplied by fi, right? This is basically a contraction, if you like, of this summation here. But this, you can also write this as the gradient. This is grad v dot f, right? If you take all the f's, the f here as, you know, as vectors, and the grad v here is the derivatives as vectors. If you dot them, you get this summation here. So this is telling us that the derivative of v with respect to t along x, see, this is, we are having the v, the x ones here. Even though we don't know what x is, we don't know the solution, but this is saying that the derivative of v with respect to t along x of the nonlinear system is known, even though we don't know the solution x itself. So that is significant. Okay, so when you construct a Lyapunov function, the Lyapunov function is not the solution, but it's, you can get the gradient of the function, the Lyapunov function, along the solution. Even though you don't know the solution, you know the gradient of the Lyapunov function along the solution. All right, and that is how the Lyapunov function is sort of related to the solution of the nonlinear system. Okay, so this is an important observation. Grad v dot f is actually the total derivative. Note that the theorem, basically the conclusions of the theorem, are based on the total derivative of v with respect to time. Okay, this is also important, right? So in general, it is actually quite difficult, very difficult to find Lyapunov functions for a given system of equations. When you have a nonlinear system of equation, there is no formula, there is no direct method that tells you that this is how you construct it. Okay, so that is one of the difficulties of practically using Lyapunov functions. But it is sometimes possible that you can guess a solution, you can guess, sorry, a Lyapunov function from, the geometrical considerations of the problem at hand, or from the physical considerations. Let's say from, energy conservation analysis, or some kind of analysis from the system itself. You can come out with a function that you could use as a Lyapunov function to analyze the stability of the equilibrium points of the nonlinear system. So the v's, even though this v is paramount, right, there is no direct way of finding it. So in most of the problems that you will be solving, you'll be asked to, let's say, construct a Lyapunov function that looks in a certain form, and then you would have to apply the theorem, or you are given one and you are asked to use it to analyze the stability of the equilibrium points. Okay, so for now you don't have to worry about coming up with a Lyapunov function for any practical problems, but that is the difficulty that you face when you are actually solving a real practical problem. How do you construct and come up with a meaningful Lyapunov function that can be used to analyze the system? Okay, good. So the next few lectures will be 3 examples. Okay, so example 1 will be here. I have another example 2, and then I have a last one. So in the next video that I'm going to do, I'm basically going to do 3 examples to illustrate how you apply the theorem. So try to understand the theorem, all the conditions of the theorem, and then you will understand these examples and how you apply it. Okay, so I'll see you in my next lecture.